Hey there, it's Shannon Math Chick Myers, and today we'll be looking at vector valued functions. So let's go ahead and warm it on up and check out these limits. We'll be looking at some limits today. So pause the movie, warm it on up, and then see how you did. Okay, let's go ahead and see how it went. There's a couple different ways one can do this. Why don't we go ahead and for this one we'll go old school on it. We can get our denominator to match our angle. So we basically multiply by 1, 2 over 2. Then that limit is just going to end up being 1. So the output of this whole limit right here is 1. And by that special trig limit, and we end up getting a result of 2. So, cool so far? All right, let's take a look at this one. If we plug in 4, you'll get 0 over 0. It'll be indeterminate. So let's just, let's go ahead and see. Since we do have 0 over 0, which is indeterminate, why don't we go ahead and use L'Hopital's rule. So this will be equivalent. So L'Hopital's rule basically says if you get a certain type of indeterminate form, 0 over 0, plus or minus infinity over plus or minus infinity, then this limit is going to be equivalent to the limit of the derivatives in the numerator and denominator. So we'll have the limit as t approaches 4 of 2t, because that's the derivative of the numerator, over 2t minus 4. Cool so far? And so now we're getting there. We just need to, well, you could differentiate again actually, because we would again get 0 over 0. So I'm going to apply L'Hopital's rule again, and that'll be equivalent to the limit as t approaches 4 of 2 over 2, which gives us a result of 1. All right. So now let's check out this one. As x tends to infinity, do you see that first term and the second term are going to tend to 0? So we'll end up getting 0 for the first term, because that's 1 over e to the x, and so that would make a very large denominator, right? And then 6 over x, that's going to tend towards 0. Now, as arctangent goes, as x tends infinitely to the right, what does arctangent end up at? Beautiful, pi over 2. So, at the end of the day, we have a result of pi over 2 for the last one. Groovy? All right. So now let's take a look at vector valued functions. These are really pretty groovy. Hopefully you'll find them to be as cool as I do. So let's just take a look. Let's say you've got y, you've got x, something like this. And I'm just going to take a look at this in the plane. And let's suppose you've got some curve. So you've got this curve, and we'll call this curve C. Now, a vector valued function is really awesome. What'll happen is you'll have some r vector, okay, and we'll define this in the definition below. But what happens is you end up having, this could be, I'm sorry, This could be like r at t0. And then maybe you've got some r vector at t1, right? And then continuing on and on and on, right? You can have the infinitely many vectors, but you always, can do these from the origin. So call this one r at t2, and then some r at t, we'll just call this one some tn, okay? And so anyway, these vectors, this is how you would make a function vector valued, and this is what it would look like. So let's take a look, a vector valued function. So a function of the form r at t equal to f at t times I plus g at t times j. This is in component form. What would we have? This would be equivalent to, beautiful, whoops. This would be equivalent to f at t, comma, g at t, and this is defined for the plane. And then you can also have r at t equal to f at t times I plus g at t times j plus h at t times the vector k, which in component form would just give us, f at t, g at t, h at t, and this is in space. Now, these are the format, these are vector valued functions where the component functions, f, g, and h, or just f and g, are real valued functions of the parameter t. The domain is considered to be the intersection of the domains of the component functions f, g, or f, g, and h, unless stated otherwise. So let's take a look at an example. Let's find the domain of the vector valued function. So what do we have here? We have r at t is equal to the square root of 4 minus t squared times I plus t squared times j minus 6t times k. Right? So let's take a look. We have our f at t is equal to, the square root of 4 minus t squared. Okay, so what do we have going on here? I mean, isn't this just a semicircle, right? The positive upper half of a semicircle. So this function here would be, you have like your x and your y. The radius would be, actually that would be t and f at t. And your radius is 2. So your picture is just going to be, it would be inclusive from -2 to 2 for a domain, right? There we go. Good enough. So the domain for this guy is from -2 to 2 inclusive. So let's look at the other one. So for g at t, there any g at t is equal to t squared, right? So there's no, the domain for this guy is just what? Minus infinity to infinity. There's no restrictions. And h at t is equal to, call it negative 6t. And so again, there's no restrictions on this domain. It would be from minus infinity to infinity. So the intersection of these three domains is going to be what? So the domain for r at t is going to be the intersection of these. So it would go from negative 2 to 2 inclusive. Cool, cool? Okay, next up, let's see what we have going on. Sketch the curve represented by the vector valued function. So here we have r at t equals quantity 1 minus t times I plus the square root of t times j. So the intersection of these domains, that for f at t and g at t, right? So remember, f at t is 1 minus t. So the domain for that would be all reals. And g at t is equal to the square root of t. And so the domain for that is good, 0 inclusive to infinity. So the domain for r is going to be zero to infinity, where 0 is included. Cool, cool? All right, so r at, let's just plug in some values, right? So r at 0, so we're plugging in values for t, right, would be 1 minus 0 times I plus the square root of 0 times j. So all I'm doing here is we've got this input of t. Oops. And so now I just put in a 0 wherever there was a t. So we're going to end up getting r at 0 is equal to 1 times I plus 0 times j. And what's that going to give us, you think? Just the I vector, right? So let's see. I think we need to have a really large scale. So if this is t and this is, so our inputs are t and then our outputs are going to be our vectors, right? So I'm just going to call it y, all right? So then let's see. Let's say that each of them will have a scale of a half, so that would be 4. 1, 2, 3, negative 4. And then 1, 2, 3, 4. And 1, 2, 3, negative 4. So what will happen is our very first vector that we can graph is this one here, right? This is just our I vector. Cool, cool? All right, so then next up, why don't we do r at 1? So that's going to be what's going to happen this time. 0I, right? And then plus 1j, which of course is just j. All right, so then that vector will be like this. All right, and next up we have, why don't we do r at, I guess 4. because that's a perfect square. And then we'll get 1 minus 4 is negative 3i, right? And then plus 2j. When we do this one, that's going to be 1, 2, 3, 2, and that's from the center. And you see, as we, keep going, if we had put in like r of 9, right, we would have ended up. Well, I guess we can do that. Let's try r of 9. I think it'll work. It'll take us way out of our picture, but that's okay. R of 9 will be 1 minus 9 would be negative 8i, and then plus 3j. So then our vector would be somewhere way out here, right? Cool. And so then our curve is going to look like this. It follows along, and it's going, you have your direction, and it follows along, something like this. And then we know the direction it's going is this way because that's the way our vectors are pointing. And it would just keep going on. Cool? All right. So let's take a look at our next example. So this one is in space, right? And this, you're going to love this, all right? So notice that, let's see, the domain of the cosine function is all real numbers, the domain of the sine function is all real numbers, and the domain of t over 2 is all real numbers. So the domain for r is all real numbers, the set of all real numbers. So r at 0, I'll write this out a bit, would be 3 times cosine 0 I plus 4 times sine 0 j plus 0 over 2 times k. And again, I'm just plugging in. Wherever I see a t, I'm plugging in 0. Good so far? So that's going to just give us what? Cosine 0 is 1, right? So I believe we'll get 3i. Sine 0 is 0, and then the k would 0 out. So we'll just have 3i. Good so far? All right, so now let's take a look at, I don't know, how about pi over 2? So r at pi over 2 is 3 times cosine pi over 2 times I plus 4 times sine pi over 2 times j plus pi over 2 times k. And that's going to end up being, the cosine function will 0 out, right? And sine of pi over 2 is 1, so I believe we'll get 4j and then plus pi over 4k. Good so far? All right, and then how about r at pi? That'll be, and here's where we plugged in. So now we'll get negative 3I, and then the sign function zeroes out, and then plus pi over 2 times k. And continuing, we'll want to, get sort of a feel for what's going on. If you continue in that, let's at least do 1 rev. So r at 3 pi over 2 would be, can I just go a little faster now? Cosine 3 pi over 2 zeroes out. And so then I think we'll get negative 4j. And then we'll get 3 pi over 4 times k, and r at 2 pi would be 3I plus 2 pi k. Okay, and then we're not going to drop below that z-axis, so let's just go ahead and start drawing some of these cool vectors here. So, all right, our very first one, easy peasy, 3I. Get this more thick. So that's what that first one will be. And this one was r at 0. So r at pi over 2, let's see, we ended up with 4j plus pi over 4k. Pi over 4 is about 0.79. So we'd be just about maybe here. And then r at pi, negative 3I plus pi over 2 times k. Pi over 2 is about 1.57. Be about here. And continuing, our next one was negative 4j plus 3 pi over 4 times k. So then that 3 pi over 4 is going to be about 2.36. So j will be back here, and then about here. Okay, let's take a look. So r at 2 pi, oh, you know what? I made a mistake here, right here. That should have been what? Pi times k. Whoops. So, so let's take a look. Pi is what? 3.14-ish. And so we'll see where we're at. So 3 I think that's about here. All right, so we just so you can kind of see where we were at. This one, this first one here was r at 0. This was r at pi over 2. This guy was r at pi. And over here we were at r at 3 pi over 2. And now we're at r at 2 pi. So let's see what our curve is looking like. So we've got it going like this. It kind of comes over here. And it'll be over here. And then now it's over here. Whoops. Coming back over here. So now let's do a few more just to kind of see where we're at. So we've got, if we do r at 5 pi over 2, right? What's going to happen is we're going to get the same values outright for our trig functions as r at pi over 2, but the k is going to be higher. So we'll end up getting, for r at pi over 2, we're going to end up getting 4j plus 5 pi over 4 k, and 5 pi over 4 is going to be so that'll give us about 3.92. So graphing that one, we'll have so r at 5 pi over 2 is going to give us 4j, and then plus 5 pi over 4, which is approximately 3.9-ish, times k. So going over and graphing, let's see what it looks like. So 4j, and then 3.92-ish, about here, a little lower. And then r at 3 pi is going to be negative 3i, and then plus 3 pi over 2 times k. And making our picture. Let's see, 3 pi over 2 gives us what? 1.5, about 4.71. That'll be about here. And you see how it's going to keep on spiraling, right? The further we go. So we'll end up, let's draw more of our curve here. So we end up going here and here. And then it'll just keep going on spiraling and on, like that. Isn't that kind of cool? Right? So let's see if we can graph that in the 3D grapher. So again, we're using CalcPlot 3D. So let's get rid of this one. And then let's select, get close. Let's go ahead, just take this guy out, and then we're going to select a space curve. I bet that's going to be it. Yep. Okay, so what was our x of t? It was 3 times cosine t. And then we had 4 sine t. And then we had t over 2 t over 2. Isn't that cool? So we can, and you can change your, you can change your axes. So if we did x and y, let's see, x is just gonna -3 to 3 because of it's periodic, and then y would be -4 to 4, and z basically, actually z can be negative. I think I said it couldn't be, so let's do negative, I don't know, 20 to 20, and then so it looks like this. Isn't it awesome? Now, one kind of thing is you can animate your trace, right? So if you trace along, you got t is 0, and see, isn't that really cool? How it's going. All right. Anyway, enough fun. Let's go back. And another thing that's cool on this one is that then you can just zoom it in, check it out. Groovy, huh? All right. So next up, we come to the definition of the limit of a vector valued function. So if r is a vector valued function such that r at t is equal to f at t times I plus g at t times j, then it turns out that the limit as t approaches a of r at t is equal to the limit as t approaches a of f at t times I plus the limit as t approaches a of g at t times j, provided f and g have limits as t approaches a. And if you're in space, right, where r at t is f at t times I plus g at t times j plus h at t times k, then what do you think we're going to have? We're going to have the limit as t approaches a of r at t is going to be the limit as t approaches a of f at t times I plus the limit as t approaches a of g at t times j plus the limit as t approaches a of h at t times k. Cool, cool? And of course these limits have to exist. So, okay, what the heck does that really mean? So let's say we have, let's say that you've got this r at t, and again, we'll just take a look at this in the plane, right? So you've got r at t in the plane, and so let's say our origin is here, and let's suppose that our actual limit, okay, is here, and we're on a plane curve. So this is and this limit, of course, is going to come out as a vector. And so, let's say our r at t trends like this. So this is r at t. And then you've got some curve going on. So you've got this plane curve going on. Good so far? All right, and then so what's happening is that as t is approaching A, so you could keep as you go along the plane curve, right? These are your r vectors at some t, etc., right? And they're going to get closer and closer and closer to this L vector and this is basically as you're kind of going along here, what's happening is T is approaching some A. Cool so far? So what's happening from the other end here now, what's going to be happening so now let's take a look is you've also got this stuff going on here, right? And that part, I don't know if you remember from, limit definitions of times past, right? That is basically the difference between your actual r at t minus the limit vector, okay, in that color. Cool? All right, so I know that's a little complex, but I thought I'd give you a little picture of it. So definition of the continuity of a vector valued function. A vector valued function r is continuous at the point given by t equal to a if the limit of r at t exists as t approaches a, and if the limit as t approaches a of r at t is equal to r at a. So just an extension on your continuity definitions. And then a vector valued function r is continuous on an interval I if it's continuous at every point in the interval. Okay? So evaluate the limit and determine the interval or intervals on which the vector valued function is continuous. So here we go. The limit as t approaches 1. So remember, you can bring that limit in. So here, if you wanted to take a look that f at t is equal to natural log at t, right? And so the limit as t approaches 1 of natural log at t using direct substitution is natural log at 1 which is equal to 0. Good so far? Well, g at t is equal to 1 minus t squared over 1 minus t, and then that's going to be, if we take the limit as t approaches 1, that's going to be indeterminate, right? So you'll get 0 over 0. So we can use, we'll just write it out again, 1 minus t squared over 1 minus t. So here, if we use L'Hopital's rule, because you do get 0 over 0, what's that going to be? It's going to be the limit as t approaches 1 of negative 2t over negative 1, which is just going to be, by direct substitution now, negative 2 times 1 over negative 1 is positive 2. Cool so far? And h at t equal to arc sine at t. So the limit as t approaches 1 of arc sine at t is equal to the limit, or not the limit, we can do direct substitution here. So we would get arc sine at 1, which is equal to pi over, which is equal to pi over 2, because remember the range of the arc sine function is going to be from negative pi over 2 to pi over 2. So at the end of the day, what do we find? Well, we find that L, right, our limit vector, is going to be 0 times I plus 2 times j plus pi over 2 times k. Good so far? Now, let's think about the domains of our different functions. So for f at t, isn't our domain from, so we'll have domains, right? So for f at t, the domain is from where to where? Beautiful, 0 to infinity. G at t, we just can't have t equal to 1, right? So g at t would be minus infinity to 1 union 1 to infinity. And then h at t, well, the domain for the inverse sine function is set from negative 1 to 1 inclusive, right? So let me make sure I'm showing you that we did actually finish this one. So our L vector is just 2j plus pi over 2k. And that part we had finished. Good so far? And then the continuity part is what I'm doing over here in the pink, right? So what is the overlapping domain? We've got 0 to infinity, everything but 1, and negative 1 to 1, right? So isn't that overlapping domain going to be 0 to 1, non-inclusive? Good. So and determining the interval that this function, vector valued function, is continuous, the vector valued function is continuous on zero to 1, non-inclusive. Groovy? All right. So I believe that wraps it up for today. Awesome. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. Bye.